Hi student, this is chapter 22, black holes. The study of black holes starts with the study of theory of relativity. There are two basic axioms of theory of relativity. The two axioms of theory of relativity are that the laws of physics are the same for all observers in uniform motion relative to one another. This is called principle of relativity. Secondly, the speed of light in vacuum is the same for all observers regardless of their relative motion or the motion of the source of light. For example, this picture shows the difference between the speed of light and the speed of a physical object. For example, in this case, the batter hits the ball and the ball is moving away at 30 meters per second from him. So according to him, the measurement of the speed will be 30 meters per second. However, the fielder is approaching the ball, and because her speed is 10 meters per second, because of that, from her point of view, the ball is approaching her at a speed of 40 meters per second. So the speed of the same ball is different for different observers depending on their motion. However, when it comes to light, on the left, we have an astronaut who is shining a flashlight, and he measures the speed of light to be 3 times 10 to the 8 meters per second. And there's another spaceship approaching the astronaut from the right, and it is moving at the speed of 1 times 10 to the 8 meters per second. If we apply the same logic, then the speed she should measure should be 4 times 10 to the 8 meters per second. But turns out that when she'll measure the speed of light, it will be 3 times 10 to the 8 meters per second. This has wide-ranging effects. The whole theory of relativity is built on it. It has several effects, such as length contraction, time dilation, things that are moving fast, close to the speed of light. For them, the time slows down. So there's special theory of relativity, which was first proposed by Einstein in 1905. Special theory of relativity is called special theory of relativity because it only deals with the special cases where the speed of the objects is constant. They are not changing their speed, they are not accelerating. However, he kept researching the topic and came up with a more all-encompassing theory later on, and that was called the general theory of relativity, and that included effects of gravity as well as acceleration. In finding his general theory of relativity, one of the basic fundamental pillars of his general theory of relativity was the equivalence principle. And the equivalence principle says that it is impossible to distinguish between an acceleration and gravity. So here is a description of general theory of relativity. It can be described by 3 simple sentences. A massive object curves the space-time around us. Far from the object, space-time is nearly flat. Close to the object, the curvature forms a well. In Einstein's picture of gravity, other objects sense the curvature and are drawn into the well. So in the center, we have something like a black hole or the sun, and around it is circling a planet or a star. Okay. So according to Einstein's theory of gravity, it is the structure of the space-time that causes it to go in a circular path, not an actual force of gravity that extends over vacuum. Another way to describe general theory of relativity is mass tells the space-time how to curve, and the space-time tells the mass how to move. There have been various tests of theory of relativity, and theory of relativity has been always proved, has always passed those tests. One of the predictions of Einstein's theory of relativity was bending of light by gravity, and this was detected in the gravitational deflection of light by the sun by an experiment that was done during the solar eclipse in 1919. Another test is the precession of Mercury's long orbit. This concept was, or phenomena was known already, and it was not explained by Newton's theory of gravity. However, when Einstein came up with his theory of relativity, the calculations done in accordance with theory of relativity explained the precession of Mercury's orbit. And the third one was slowing down of time due to gravity, and that was also proved in the Pound-Rebka experiment. So what is a black hole? Black hole is the curvature of space-time, infinite curvature of space-time. So in the previous chapter, we talked about neutron stars, and we found that their limit was 3 solar masses. So at 3 solar masses, at slightly less than 3 solar masses, the neutron degeneracy pressure stops the contraction of the star, and it comes to a certain size and becomes stable. However, if after the supernova, if the mass of the remaining core is greater than 3 solar masses, then even the neutron degeneracy pressure is not able to stop the contraction of the star, and it keeps on contracting, getting stronger and stronger gravity, and therefore contracting more, and it contracts into a point with an infinitely large amount of gravity, and that is what is called a black hole. So to understand the meaning of a black hole, we have to understand about the escape velocity. All objects in the universe which have gravity, they have an escape velocity. The escape velocity is the velocity with which you can throw an object from the surface of that astronomical body. If you throw the object at that velocity, then it will be able to escape the gravity of the object, and it will never come back. Different objects have different escape velocities. The bigger the object, the greater the escape velocity, such as, for example, the escape velocity from Earth's surface is 11.6 kilometers per second. As the gravity grows stronger, the escape velocity gets bigger and bigger and bigger. However, as we know, there is a limit to what maximum velocity any physical object in the universe can have. And so there comes a time when the escape velocity becomes greater than the speed of light. And then at that time, nothing can escape from the grips of gravity. And that's when we have formation of a black hole, because not even light can escape from it. And so the object looks dark. So the star keeps on contracting and becomes an infinite singularity. a point mass with infinite gravity. However, there is a radius around it, which is called Schwarzschild radius, and that is the radius of no return. When an object gets to that radius, that is the point of no return. There could be black holes, and objects could get in the vicinity of a black hole, but still be far enough away that they don't get sucked into the black hole. In fact, every galaxy has a supermassive black hole at its center, but all the other stars in the galaxy are able to stay not getting sucked into the black hole. And this is because they are outside the Schwarzschild radius. So the Schwarzschild radius is given by this formula, IS is equal to 2gm over c squared. Schwarzschild radius is the point from where not even light can escape. Where are the black holes? A supermassive black hole is present at the center of every galaxy. There are black holes in supernova remnants. We talked about how supernovas cause neutron stars to form. Sometimes when there is a supernova explosion that has happened, we can look in the different parts of the sky, and sometimes we can see a remnant of supernova. It looks like a bubble made of gas and dust, and it's a constantly expanding bubble because of the explosion. If we look at the center of that remnant, we might find a neutron star. However, if we don't see anything at the center of it, then that means that the object has turned into a black hole. So we would have to look more closely and look for other evidences of the presence of a black hole. There could be black holes in binary systems. You could see one big star wobbling around at quite extreme speeds. However, you cannot see the companion star, and that could be because although it has a very strong gravity, but it has a very small mass, a very small size, so we cannot see it. So then we would look closely, and by other calculations, we would be able to guess that there is a black hole as a partner in the binary system. And sometimes, even though we cannot see the black hole, there are other things such as hot accretion disk and radiation jets coming out of the black holes. And those are things that we can see and therefore identify the presence of a black hole. So here are the methods of detecting black hole: orbital velocity of surrounding stars or partner objects. So especially in the centers of galaxies, we can see that some stars are moving very fast, are spinning very fast around the center. It is possible to calculate the gravity of the object in the center. And if with the gravity, we can calculate the mass. And if an immense amount of mass is packed within a very small space, then we can guess that there is a black hole there. Gravitational lensing, the deflection of light by gravity is done by black holes, and that causes a lensing type of effect, so that when a black hole passes in front of or in between the Earth and view of a galaxy, it distorts the view of how the background galaxy looks like. And that is called gravitational lensing. There's microlensing, and then there's accretion disk and Hawking radiation jets, which also give away the position of a black hole. Right, see, these are just more detailed explanations of the different points, the different ways of observing black holes. The binary system, the accretion disk, the radiation jet, and this is the gravitational lensing. The above picture is a simulation of what you could expect if a black hole passed in front of a galaxy. What would we expect if this is a sort of thought experiment of what would happen to an astronaut if they got very close to the Schwarzschild radius of a black hole? First thing that would happen is their bodies would get stretched out. The very strong gravity and the change in the strength of gravity would be so strong that it would cause a tidal effect where it would stretch the astronaut vertically, causing them to become, their bodies to get stretched out. This is called spaghettification. Then there would also be time dilation because of gravity. The closer and closer that they get to event horizon, their time would move more and more slowly until when they get to event horizon, the time would stop moving. There would also happen a gravitational redshift. We would keep looking at the astronaut and we would be able to see the astronaut because light falling on their bodies is reflected and coming to our eyes. But as they get closer and closer to the black hole, the gravity of the black hole would make it harder and harder for the light to be returned to us. And the wavelength of the light traveling towards us would get stretched and lower in energy, causing it to shift towards the red side of the spectrum. And that is called gravitational redshift. And so the image of the astronauts would look more and more dim and red until we would stop seeing them. This picture shows the series of steps in how a star changes into a neutron star and then into a black hole. And at each of those steps, the gravity becomes more and more intense, and it causes greater and greater deflection of the light being emitted from it until at one point the light just cannot escape the black hole. This is the same kind of picture that you saw earlier. Only difference is this is for a black hole, and black hole is described often as a tear in space-time. The curvature, the well formed by the black hole is so deep and so sharp that it causes a tear in space-time. Here is one very well-known area where we have detected and we know that there is a black hole for sure in the Cygnus X1 system. All right, here are the last few slides. There are various speculations about how black holes could affect time, and they could be our connections to other universes through Einstein-Rosen bridge, or they could also be wormholes that let us connect infinitely far away parts of a galaxy with a wormhole. And with a wormhole, we would be able to travel from one part of the universe to another part, essentially getting to the other part faster than the speed of light. So with that, we end this chapter on black holes.